In this video, we'll be looking at the preparation of alcohols. We'll be starting with a review, looking at preparation of alcohols by nucleophilic substitution and preparation of alcohols from alkenes.
One way that we can prepare alcohols is by doing nucleophilic substitution. So depending on the structure of our substrate, if we have a carbon connected to a leaving group and we have something that can act as a nucleophile, in particular a hydroxide or water that can act as a nucleophile, then this can add here, kicking out the leaving group, and this would be SN2 substitution. Or, again, depending on the structure, if we have water rather than hydroxide, so we have a much weaker nucleophile, then the leaving group can leave, giving us a carbocation intermediate, and then water can add, acting as a nucleophile, the water can add, giving us OH2 plus, and then a proton transfer will give us our alcohol. So here we have a few examples. If we have our simplest alkyl bromide, methyl bromide, this can be treated with sodium hydroxide in ethanol and water. So make sure that we're focusing on the most reactive species, right? In other cases, we can have ethanol or water could act as a nucleophile, but we also have hydroxide present, and that is the strongest nucleophile that's in here. So this is going to be the nucleophile. It is going to add here, kick out bromide, and we get methanol. So because this goes through SN2 substitution, we have to have backside attack, and that leads to inversion of configuration. In this case, it doesn't really matter because we're not generating a chirality center, but still keep that in mind. Now, what if we have a bulkier alkyl halide? This one is a tertiary alkyl halide. If we treat this with sodium hydroxide, well, this is a very strong base, but it can't fight its way in here because these groups are too big. So instead, this is going to settle for acting as a base. It's going to grab off one of these protons. These electrons will fold in here to form a double bond, pushing out bromine as a leaving group. So we're not making an alcohol here, we are doing an E2 elimination. So keep in mind the competition between substitution and elimination. Now in our third example, we have seen ways that we could take a tertiary alkyl halide and convert it to a tertiary alcohol. And this is where we need to use a very, very weak base. So rather than using hydroxide, we can use water. This is such a weak nucleophile that it's not going to attack. Instead, bromine gets sick of waiting around. Bromine decides to leave, and we get this carbocation, and then water will add. All right, so just as I mentioned up above. And then another molecule of water can act as a base, grab off one of these protons, put these electrons back here, giving us an alcohol. So alcohols can be prepared by nucleophilic substitution on methyl or primary alkyl halides or alkyl tosylates using hydroxide, or on secondary or tertiary alkyl halides or alkyl tosylates using water. The first method by which we can convert an alkene to an alcohol is acid-catalyzed hydration. So this is an example of electrophilic addition where the alkene acts as the nucleophile sharing electrons with an electrophilic species. The net result is the addition of hydrogen and the OH group across the double bond. If we're starting out with an unsymmetric alkene and we treat this with sulfuric acid and water, we could add the H here and the OH here, giving us the first product, or the H here and the OH here, giving us the second product. Let's take a look at the mechanism to figure out what's going on. So it's electrophilic addition, which means the alkene is going to share electrons with this proton, because remember, when we have sulfuric acid in water, it's the same thing as saying we have H3O+. These electrons are going to go over here. So if the door opened, if the alkene door opened so that the hinge was over here, that means the blue hydrogen became connected to this carbon, which leaves this as the carbocation. If this is the hinge and the door opens to the left, then the blue hydrogen becomes connected to this carbon, and this is left as the carbocation. If we have this carbocation and water adds here, then we get this protonated alcohol intermediate, and then another molecule of water can grab off a proton, put these electrons back onto the oxygen, giving us this. The alternative from this carbocation, water would add here, giving us this protonated alcohol, and then water can grab off a proton, put those electrons back onto the oxygen, and that gives us this product, right? So this one corresponds to this, and this product corresponds to this one. So the major product will be the first one, because that one arises through the more stable carbocation intermediate, right? So because the hydrogen becomes connected first and it leads to the formation of a carbocation, then the hydrogen is going to add to the carbon that already has more hydrogens. So we're talking about Markovnikov addition, which can be phrased in a million different ways, but basically when you're looking at an unsymmetric alkene, the hydrogen becomes connected to whichever alkene carbon has more hydrogens to begin with, and the other group becomes connected to the alkene carbon that had fewer hydrogens to begin with. But the reason for Markovnikov addition is that it proceeds through the more stable carbocation intermediate. So the good news is that we can predict what product is going to form. We know that we would have Markovnikov addition, but one of the drawbacks is that since we have a carbocation as an intermediate, it is possible for carbocation rearrangements to occur. So that's something that you have to be on the lookout for. Now, this particular reaction also should look very familiar because it is the opposite of a reaction that we looked at last semester for the preparation of alkenes. So an alcohol can undergo acid-catalyzed dehydration to give an alkene. And if you look back at the mechanism, you will see that that each step is the opposite of what we're looking at here. And really, we're thinking about Le Chatelier's principle, and we can get the reaction primarily to the right or primarily to the left by tweaking the reaction conditions. So this one's important in part because it is analogous to other electrophilic addition reactions we've already seen, and because it is related to a reaction that we looked at last semester, dehydration. But in some cases, there are challenges because of the strong acid, because of the carbocation and the possibility of carbocation rearrangement. So there are a number of other methods that have also been developed to convert alkenes to alcohols. The next method that can be used to convert alkenes to alcohols is called oxymercuration demercuration. The alkene is treated with mercury acetate, and this undergoes an electrophilic addition of mercury, and then that mercury-containing intermediate is treated with sodium borohydride for the demercuration step. So I want to show you the intermediates, though you're not responsible for the detailed mechanism. Here we have 1-methylcyclohexene, and if this is treated with mercury 2 acetate, it forms an intermediate that looks like this. So we have mercury connected to one equivalent of the acetate, and we have a positive charge. So this is kind of like a cyclic bromonium ion. So this is an intermediate. Now you have water present, still in the first part of the reaction, so the water can now act as a nucleophile, opening up this three-membered ring, and it tends to add to the more substituted carbon. So this is still an intermediate. Here is our methyl group and our OH2 plus, and now our mercury acetate species is connected to the other alkene carbon. This will do an acid-base reaction to get the OH and the mercury acetate. And then with the second step, sodium borohydride, here a hydride replaces the mercury group, giving us this compound. So the net result is that H and OH have added across the double bond, and it proceeded by Markovnikov addition because the alkene carbon that started out with more hydrogens, 1, got the hydrogen, and the alkene carbon that started out with fewer hydrogens, 0, got the other one. So oxymercuration, demercuration, it provides an alternative to the acid-catalyzed hydration. It gives Markovnikov addition, but because there's no carbocation intermediate, there's not the risk of a carbocation rearrangement. I'm not going to ask you to show me the mechanism. I just shared this in case you were curious. What's more important to me is that, number one, you recognize the conditions for oxymercuration, demercuration, and you know that this leads to the addition of H and OH across the double bond, and that you do so with Markovnikov addition, which means for this compound, when this undergoes oxymercuration, demercuration, we will get this secondary alcohol as the major product, not this one. The third method by which an alkene can be converted to an alcohol is called hydroboration oxidation. So an alkene might be treated with borane and THF, or it could be diborane, B2H6. So the first step is the hydroboration, in which the alkene is converted to an organoboron species. And then in the second step, the oxidation. So this is treatment with hydrogen peroxide and hydroxide. This converts the organoborane into an alcohol. What about stereochemistry? So here we are looking at the same alkene we used a couple slides ago. And so if this is treated with borane THF, followed by hydrogen peroxide and hydroxide, we have the possibility of forming two different products. So we could add the H here and the OH here, giving us the first product, or H and OH, giving us the second product. So hydroboration leads preferentially to the second product. So this is non-Markovnikov addition. Non-Markovnikov addition. So in this way, hydroboration oxidation complements oxymercuration demercuration because you get the opposite regiochemistry. So the bad news is it's more stuff to remember, but the good news is it gives you the power to choose which product you get, and you can control that by selecting the proper reagents. So another thing about this reaction, which isn't obvious from this particular example, it is non-Markovnikov and syn addition of the H and the OH. So we're not going to look at the whole mechanism, but there are a couple of features that I wanted to point out. So for the formation of the organoborane, the BH3, for example, will interact with the alkene. It leads to this type of transition state. So we have a little square. Whatever is diagonally across from the boron, this picks up a partial positive charge because the boron has a partial negative. Same thing over here. Boron has a partial negative, so the carbon diagonally across has a partial positive. So one aspect of the regioselectivity has to do with which carbon can better bear this partial plus charge. So this carbon is less substituted, whereas this carbon is more substituted. So based on electronics, this is preferred. But there's another feature as well, and that would be sterics. So to begin, this alkene is treated with BH3, for example, and so this R group is a hydrogen and a hydrogen. So if we look at sterics, then if the borane lines up this way, then we have a hydrogen that's near the carbon with the hydrogens, and we have a boron that has additional hydrogen groups that is closer to the methyl groups. So this is going to be a little bit crowded. Whereas in the other possibility, we have our hydrogen lined up with a more substituted carbon, and then our other hydrogens are lined up with other hydrogens. So the crowding here is less severe. So by sterics, this is also preferred. So that explains the regiochemistry. Also keep in mind this little square transition state because both the hydrogen and the boron add to the same face of the alkene. So we have syn addition of the hydrogen and the boron. If the boron added to this particular face of the alkene, then this is where the oxygen will also be connected, right? So syn addition of the borane leads to syn addition of the H and the OH across the double bond. This is another reaction that involves, okay, so from this alkene, it reacts with BH3. This is the preferred transition state leading to this intermediate. But this can now interact with another molecule of alkene, and so we're going to form a dialkyl and then a trialkyl borane. 3 molecules of alkene can react with each molecule of BH3. And so this is what we have at the end of the hydroboration step. And then with oxidation, we get back 3 of these, where this carbon that was connected to the boron, it becomes connected to an OH. So hydroboration oxidation gives us non-Markovnikov syn addition of H and OH across the double bond. So let's compare these 3 different methods for the conversion of an alkene to an alcohol. The first one is acid-catalyzed hydration, and this will give us Markovnikov addition of H and OH across the double bond. So that will lead to 1-methyl cyclopentanol in this case. In comparison, the same starting material, if you carry out an oxymercuration demercuration, this one will also give the Markovnikov product. And finally, same starting material, if we carry out hydroboration oxidation, this one will give us non-Markovnikov syn addition of H and OH across the double bond. So it is the opposite regiochemistry compared to our top 2 products. Unfortunately, if both of these add from the back face, well, it's also likely that they would add from the front face. So you will get a mixture of enantiomers. But still, the H and the OH are connected to the same face. So it's important to keep in mind the 3 different methods: acid-catalyzed hydration, oxymercuration demercuration, and hydroboration oxidation. You need to recognize the reaction conditions, and you need to know enough of the mechanistic details just to be able to predict the major product. Okay, knowing that this goes through a carbocation, it leads to Markovnikov addition, but there could be a risk of carbocation rearrangement, right? This one goes through that cyclic mercury species, which leads to, again, Markovnikov addition, so the OH becomes connected here. Because there's no carbocation, there's no risk of carbocation rearrangement. And then in this case, with hydroboration oxidation, because of how the borane adds, the H and the B become connected to the same face, and we're looking at non-Markovnikov addition as well. So a few options to prepare alcohols from alkenes.